Hey, 12th graders. This is our last lesson for our sinusoidal modeling unit. So far what we've done is we've just talked about how to evaluate sinusoidal models, how to use them, understanding the key behaviors of sinusoidal models, using that in order to understand the context of the situation. That was all lesson one. Lesson two was then solving for some unknowns within sinusoidal models, right? So like having only like one unknown or maybe two unknowns, but there was some information that was given to you. So we talked about when to plug in points, when to use specific information based off of the thing that's missing, right? If it's your amplitude that's missing, how do you use information in the context to solve for the amplitude, knowing how to break that all down. And now on our last lesson, we're talking about just how do you have completely empty models, right? So like nothing here except for telling you that it's sine. And how do you create the model just from scratch? You have nothing and you have three unknowns. So since we know what these three unknowns are, we know that A is amplitude, B has something to do with the period, and D is your principal axis. We go through and we look at the story that we're being told here, and we try and find that information from the story. Right. So the depth of water in a harbor in meters is modeled using the function of the form this. They always tell you the form that it's in because they'll always tell you whether it's sine or cosine. So just so you know that is something that's nice for this class because of SL, that they will always tell you whether it's sine or cosine. So they'll always give you this like blanket formula. Where T is time in hours after midnight, it's believed that the depth varies between 3 meters and 5 meters with a period of 12 hours. Find the depth at 3 p.m. So in order to find the depth at 3 p.m., we need to first have an equation that represents this relationship. So we were told that a period is 12 hours. Okay, that'll be great for B. We know that our period is equal to 360 divided by B. And so since our period is 12, we'll be able to plug that in over there. It says then that the depth varies between 3 and 5 meters, which means our minimum Y value is 3 and our maximum Y value is 5. So we know if we were to just like kind of draw the idea of the sinusoidal graph that our maximum is 5 and our minimum is 3. So trying to figure out a couple of pieces of information, that's the height, right? So we're talking about principal axis there as well as amplitude. Principal axis will be the number smack dab in the middle, which is 4, right? And then our amplitude will just be 1 in this case. So using this information, we're able to find out that A is equal to 1, our amplitude is equal to 1, and our principal axis, D, is equal to 4. So using just that information, we're able to find out two pieces of information, which is great. And then our period being 12 hours, realize that you also can have an equation that B is equal to 360 divided by your period. And you're going to see me taking that shortcut quite a bit because I know that is a shortcut. I'll explain it to you really quick. If you multiply both sides by B, it would be B times the period equals 360. And then you can divide both sides by the period. So, it's either B is equal to 360 divided by the period or the period is equal to 360 divided by B. Ultimately, if you wanted to know the like shortcut thought process, it's 360 divided by whatever number is associated around the period, whether it's B or the actual period. The context is that this is technically the formula, but because of mathematical operations, you can just flip them around. Okay, so since the period is 12, we do B is equal to 360 divided by 12, and that is 30. So B is equal to 30. So now we have all the information we need in order to create this model. So we go back to up here and we say, okay, well, H of T is equal to A, which is 1. So I'm not going to write it because it's just 1 times sine of. And then B is 30 times T, and then plus D is 4. Which feels like we've just accomplished something huge, except for the fact that we're not done yet, because what we're technically being asked to do is find the depth at 3 p.m. So we need to go ahead and plug in something for t in order to solve for this. What will we be plugging in for t? The number that we should be plugging in for t is 15. T should be equal to 15 because T is hours after midnight and 3 p.m. is 15 hours after midnight. So just be really careful there. I would imagine that the IB would anticipate a lot of students will plug in 3, and that's not what you're supposed to do. So you're supposed to find H of 15, and all that means is that you plug in 15 instead of T, and then you can go ahead and calculate that. Go ahead and calculate this on your own. When you type this in and plug it all in, it ends up giving you an exact number, which is pretty cool. We don't get that very often. It's 5 meters, which is our maximum. So we're at a high tide there at 3 p.m. Okay. In a busy harbor, the time difference between successive high tides is about 12.3 hours. The water level varies by 2.4 meters between the high tide and the low tide, and the first tide is 4.7 meters. Let HM be the height of the tide, T hours after the first high tide. So my initial thought process when I looked through this was like, okay, the time difference between successive high tides is 12.3 hours. So from one high tide to the next high tide, that's 12.3 hours, which is our period, right? So we can take this information and be like, okay, that's helpful. I can find the period. I can find B from that. And so, okay, next thing that I'll need to know is what is my amplitude and what is my principal axis. Sorry, brain fart for a second. So looking at this information, 2.4 meters between the high tide and the low tide, right? Which means the distance from the high tide to the low tide is 2.4 meters. Remember that your amplitude is how tall your graph is, but it's not how tall it is from top to bottom. It's half of that height, right? It's the height or the distance between your principal axis and the maximum, or your principal axis and the minimum. So you take 2.4 and divide it by 2, and that will give you your A. But I'm just going to right now be like, okay, that will help me with A. All right. And then it says the first high tide is 4.7 meters, which means that the height of the high tide is 4.7 meters. So we know our maximum. So if I were to kind of draw the idea visually, right? So we're trying to understand this all mathematically right now, right? Where I'm trying to make these connections or associations with things that are going into my formula. Okay, I have something for A, I have something for B. I'm still trying to figure out D, right? So I'm thinking about it very formulaically. You can also always think about it visually, and I recommend that you do that. If you're a visual person, being able to see that is important. So we know that this is a distance of 12.3. We know that this whole distance is 2.4. And we know that the first high tide, that this measure right here, is 4.7. So when we're trying to find the principal axis, we know it's going to be one amplitude down from the maximum. And I know that the amplitude is just half of this total distance. So half of 2.4 is 1.2. And so then you can kind of think about it visually here to see like, oh, okay, well, the principal axis would just be 4.7 minus 1.2, which is 3.5. So your principal axis is at 3.5. You could probably have thought about that. You might have been able to think about that and figure that out without looking at it visually, but maybe you're a more visual person, maybe you're a more algebraic person. I don't know. Only you know. And so thinking about it in both ways, when you get stuck, be like, have I represented it visually yet? Have I thought about it algebraically yet? Like trying to make sure that you're hitting both of those when you're problem solving is really important and can help get you unstuck. So finding this cosine model, we know that A is equal to 2.4 divided by 2, right? 1.2, that total distance divided by 2. We know that B is equal to 360 divided by the period. The period is 12.3. So dividing that out, we get a decimal. So if you go in here and you do 360. You can see I've done it already when I was making my own notes. Divided by 12.3, and we get this like crazy long decimal. Since we're using this formula later on, you can see that we're going to make a sketch later on. You should be leaving these values in exact. Don't write the rounded version. Leave it as a fraction. You could either leave it as 360 divided by 12.3. Technically, fractions shouldn't have decimals in them. It should be a fraction is supposed to have a numerator that's an integer, so like a whole number, and a denominator that's an integer, so no decimals, no other fractions, right? And so but you could leave it like that and that's fine. If you wanted the proper fraction, you just need to convert it into a fraction. So approximate to fraction, and you get that as your fraction. So I'm going to leave it as the proper fraction because I'm supposed to as the math teacher, but you could leave it as that if you want to. Okay, so that's B, and then D is 3.5. We puzzled out. So we're creating the model, which means now that we found these pieces, we need to actually write out the function. So H of T is equal to A, which is 1.2, times cosine of B, which is 1200 divided by 41 times T plus D, which is 3.5. Okay, so now we've created the model and now we just need to sketch the graph. It tells us the domain that we want to sketch this graph in. So first things first, I would graph this equation on your graphing calculator.